Welcome to Winning Edge. Today we will discuss solutions. Solutions have very important role to play in our daily life. Right from the beginning of our day with milk, use of deodorants, sprays, or whatever the alcoholic mixtures we use as a fuel, or drinks, cold drinks, they all are solutions. Alloys or different metals to make different our automobile components, devices. These all alloys are solutions. So we can safely say solutions are what drives the present modern industry. Now let's try to understand certain technical aspect of solution. What is solution? Solutions are homogeneous mixture of two or more than two components. So first is it's a homogeneous mixture. What is meaning of a homogeneous? Homogeneous mixture means composition of the entire solution and the properties of solution are uniform throughout the mixture. Means there is a uniformity throughout the solution. That's called homogeneous. Two important components of solutions are first solvent. What is solvent? Solvent is a component of solution that is present in excess quantity. Component of solution that is present in a other than solvent are known as solute. Like in seawater, we having different salts present like sodium chloride, potassium chloride, nitrates and sulfates of sodium and potassium in minor quantity. All these together make a seawater, which is a solution. Now, solutions can be gaseous solutions, solutions can be liquid solutions or solid solutions, depending upon the solvent present. Like here, we have a gaseous solutions in which if the gas is a solute dissolved in gas, is a gaseous solutions known as oxygen and nitrogen gas. This is the gas example. Liquid in gas is a chloroform mixed with nitrogen gas or mixed with air. Or we can say our deodorants are examples of liquid in gas. Or solid in gas is example of sublimation of camphor. These are briefly examples of our gaseous solutions. What are liquid solutions? In liquid solutions, as we saw, liquid will be present as a solvent. First, gas in liquid solution is dissolved oxygen in water, or we can having a dissolved acetylene in acetone. Liquid in liquid is our ethanol dissolved in water or glycol dissolved in water, whatever we are using as a coolant in engines in cold areas. Another is solid in liquid. We dissolve simply sugar in water. Our cold drinks are example of liquid solution of solid in liquid. Third, solid solutions. Now, as the name suggests, solvent will be solids here. We'll be having a solution of a hydrogen in palladium, where hydrogen gas is absorbed on solid palladium surface. Liquid in solid means amalgam of mercury with sodium. Here it's liquid because we know mercury is liquid at room temperature. So it amalgamates with sodium metal to give a sodium amalgam. Solid and solid are examples of alloys. We put a copper in gold to make jewelry, even silver in gold to make a jewelry. Or solid solution is example of tin and copper to make bronze. They are examples of solid in solid solutions. Now, composition of a solution can be described by expressing its concentration. If we exactly know how much of solute is present, how much solvent is present, we can quantitatively make it. We can reproduce it anywhere in the world, knowing its quantitative description. But we have different methods available to us to describe the quantitative descriptions of solution. Let's see how we'll describe the concentration of a solution. One, it can be a simple mass percentage method, volume percentage method. We can use molarity. We can use molality. We can describe it in form of mole fraction, mass by volume percentage, or parts per million. These all methods have their own properties and own applications, own advantages and own disadvantages. Let's now we look at all these methods one by one. All the 7 methods we will try to explore. Mass percentage. What is the meaning of a mass percentage? Mass percentage of a component of a solution is mass of a particular component in solution divided by total mass of a solution. It's a mass by mass. So we can say we have taken a 10 gram of a sugar, we dissolved it in a total 100 gram of solution. Solution total weight is 100 gram. So what is a mass percentage? We took a 10 gram sugar. 100 gram is the total solution mass, including everything, solvent as well as sugar. So mass percentage will be 10%. Right? Important point is it's a total mass of a solution in which the component mass that we are going to calculate for mass percentage is included. Volume percentage. It's analogous to mass percentage, but description quantity is volume, not mass. So volume percentage will be volume of a component divided by total volume of solution. %, glycol solution in water means 10 ml of glycol is present in 100 ml of solution. So total solution volume is 100 ml, which includes 10 ml of glycol. Mass by volume. This is used to describe many times when we dissolve a solid component into liquid. Another unit, parts per million. This unit is used to express trace quantities of solute present in solution. Remember, parts per million having application for very minute quantities present in solutions or gases. So here we compare 1 part to the million parts. Definition is number of parts of the component present in the total number of parts of all components in solution divided by and multiplied by 1 million. This is nothing but we are converting the total these component presence into per million. So we are simply calculating how many parts of particular component are present in 1 million solution parts. For example, seawater. Let's take an example of seawater. How much oxygen is present in seawater that supports sea life? Simplistic approach can be so now next quantity is mole fraction. Mole fraction is defined as number of moles of the component we want to understand divided by total number of moles present in solution. Mathematically can be described mole fraction of ith component of a solution or ith solute is number of moles of ith component in solution divided by total number of moles of solution, which includes solvent as well. N1 is a solute, N2 solute, and including all solvent and solutes. Using it, we describe mole fraction. Mole fraction is useful because it gives us in terms of moles, which is description of number of atoms present. Because of mole fraction, we can target the number of atoms present in a solution rather than mass, because mass for the higher atomic weight molecules can be higher, and relatively the smaller number of atoms can make a large mass for heavy atomic weight molecules. Thus, mole fraction gives us an accurate description of number of molecules or atoms present in a solution. Next quantity is molarity. What is molarity? It is defined as number of moles of a solute dissolved in 1 liter. I emphasize again, solution volume is 1 liter and moles is 1 mole. So 1 mole is a weight, right? So it is nothing but another way we are explaining it as weight by volume. Molarity is nothing but a technical way of saying weight by volume, where we are saying number of moles are fixed. Number of moles we know directly related to atomic overweight. So moles of solute dissolved in 1 liter of solution. Remember it. Let's take an example. We took our cylinder. We dissolved small salt in it. We put a 5 gram of salt in it. Knowing the atomic mass of sodium hydroxide, it's 40, 16, 17 and 23, 40. Number of moles we get 0.125 moles. So I dissolved 0.125 mole in 650 ml of water. I made up a solution by filling up to 650 ml. Now, in such a solution, what is the molarity? Volume of solution we convert first into liters. We divided it by 1000 ml, which is equal to 1 liter. We got a molarity. Number of moles dissolved per liter of solution. So molarity will be 0.192 moles per liter. That's how we describe molarity. But mind it, molarity having one issue, because here we have to measure the final volume of solution. We can make an error in terms of measuring the total volume, or let's say we do experiment in summer where temperature is high. Because of that, the liquid will expand and little mass will give mole volume. If we do a same experiment in winter, because of low temperatures, volume will reduce. We know volume reduces with temperature. So our experiments will not be that accurate with molarity. That's the challenge of molarity, where accuracy is required up to 0.0000 level. The molarity may not be ideal case. That's why another scale was derived known as molality. How it is different? Molality is defined as number of moles of solute per kilogram of solvent. You understood it now? Mass is fixed here. It is a mass by a mass quantity or description. We take a 1 mole of our solute and we measure 1 kg of solvent. Irrespective of which season you measure, solvent weight will remain the same. So we measure it 1 kg and we put it in a 1 mole of solute to get a 1 molar solution. That's how the effect of temperature was removed using concept of molality. Still, molarity is used on many cases because where the temperature variations are not that much, or we don't need accuracy up to 0.000 level. The great accuracy is not required. Moles of solute in 1 kg mass of solvent. Effect of temperature is nullified. Solubility of a solute is the maximum amount that can be dissolved in a specified amount of solvent, which depends on the nature of solute and solvent, condition, temperature and pressure, presence of any solubilizing agent, any agent that helps to improve the solubility of one particular component, or stabilizers we are just talking about.